Okay, in today's lecture, we're going to cover the next part of the section 6.6 material on surface integrals. So in this part of the lecture, we'll introduce the surface integral of a function of three variables and start to look at some applications. So to introduce a surface integral, let's suppose that we have a function f of three variables, so a function in space, and the domain of our function includes all points on a surface S. So what we're going to do for a surface integral is think about integrating a function of three variables over points on this surface. It's very similar to a line integral for a function of two variables integrated over some curve in the plane. So the way that we will start to define a surface integral is by doing the following. So we are going to divide our surface S into small patches or subsurfaces, which we will denote as S sub ij, which have area given by delta of S sub ij. So as we're moving through our definition here, let's keep track of what we're doing visually in our figure below. So we have some surface S, shown here in blue, and for this surface, we're going to divide it up into little bitty patches. So one such patch I've shown here, and the area of that patch is delta S sub ij. So we're going to divide up our surface into these little bitty subsurfaces, which we call patches, and we can find the area of each of those surfaces. We'll denote them as delta of S sub ij. Now, we will evaluate our function f at some point p sub ij star chosen within each patch. So for each of these little sub-patches that we choose, or that we have for our surface, we're going to choose a point, p sub ij star, that lies within that patch, so maybe one of its corners or edges or something, and we're going to evaluate our function f at that point, p sub ij star. And then we multiply that value of our function at the chosen point by the area of that patch, delta S sub ij, and then we will form a Riemann sum. So here we're going to sum over all possible I and j values. So that is, we're summing over all the different sub-patches, S sub ij. Now, if we let this norm of P denote the norm of the partition P of our surface into these little subsurfaces or subpatches, then we would define that norm to be the area of the largest patch. That is the largest surface area of any of my subpatches. So we would then define the surface integral of our function f over the surface S in the following way. So let's start with notation. So a surface integral is denoted by using a double integral symbol with a subscript of S. So here the subscript is denoting the surface, and f of xyz is the function that we are integrating. And we say here differential of s on the end, or with respect to surface area for this surface integral. And the surface integral will be defined as the limiting value of that double Riemann sum as the norm of our partition approaches zero. That is, as we shrink these sub-patches, or the area of these sub-patches down to zero, and divide up our surface into smaller and smaller sub-patches. So this will be the definition of a surface integral, provided that this limit exists. Now, of course, as we've seen with double integrals, triple integrals, line integrals. The formal definition in terms of the limit of a Riemann sum is not a very efficient way to evaluate these things. So instead, what we could do here is we can consider our surface S as the graph of a function of two variables. So let's suppose that we have a surface which could be described as the graph of a function of two variables. So let's say that it has the equation z is g of xy, where xy lies in some domain D of the plane. So let's say for this example that this surface S is the graph of a function of two variables, g of x and y. And it's the part of the graph of that function that lies above some domain D within the xy plane. So we can think about the patch S sub ij as lying directly above some rectangle R sub ij in a partition of our domain D, and the point P sub ij star that we were using as our representative point on the surface would be of the form x sub ij star, y sub ij star, and our z value would be defined by the function g of those xy values. So here, our little subpatch we can think of as lying directly over a rectangular region in our domain, and our representative point on the surface, P sub ij, is then of the indicated form. Now, the area of our subpatch, the ijth subpatch, delta S sub ij, can be approximated by the area which we will call delta of T sub ij, which will be the area of an approximating parallelogram that lies in the tangent plane to our surface. So for our surface S at this point P sub ij, we can find a tangent plane to the surface at that point. And within that tangent plane, we can form a small parallelogram. And the area of that parallelogram would be an approximation for the area of this subpatch delta S sub ij. So that is delta S sub ij is approximately delta T sub ij, which would be given by the square root of 1 plus g, the partial of g with respect to x squared, plus the partial of g with respect to y squared, times the area, delta A sub ij, of that rectangular region R sub ij. So we have the following then. Our limit for the definition of a surface integral then reduces to define a double integral. So let's think about why. So here we are taking the limit of a double Riemann sum, f evaluated at this point, p ij star. Well, we can define that point in terms of x and y, where our z coordinate is given by the value of g at x and y. And then our delta S sub ij is now replaced by the following approximation. The square root of the sum of 1 plus the sum of the partial derivatives of this g function squared times delta A sub ij. So adding over all ij values, we now have a limit of a double Riemann sum, which is in terms of delta A sub ij. That is with respect to area. It's now defining a double integral over a plane region D instead of a integral over a surface. So we're going to make use of that to evaluate these surface integrals. So here in our next theorem, we have a formula for evaluating surface integrals as double integrals. So here's what it says. If we have a function f of 3 variables, which is defined on some surface S, and the surface is the graph of a function, z equals g of xy, for points xy in some domain D in the xy plane, then the surface integral of our function f can be evaluated as a double integral over the plane region D, where our function f of xyz is now given by f of xy and z, since this surface represents the graph of a function, would be replaced by the function g of xy. Now our differential of s on the end, when we're converting to area, we had that differential of s was given by the square root of 1 plus the sum of the squares of the partial derivatives of the function which defines our surface, z, with respect to x and y, integrated with respect to area now. Now, of course, if we have a surface in space that would be more easily thought of as being projected down on to the xz or the yz planes, we would have similar formulas to this for those projections onto the yz or the xz plane. But in, I think, nearly all the examples we'll consider in our course, we're always projecting onto the xy plane. So let's look at some examples. In our first one, evaluating a surface integral of a function, we are asked to find the surface integral of x with respect to surface area over the surface S, which is the part of the plane 2x plus 2y plus z equals 6, which lies in the first octant. So let's see if we can sketch our surface here. So in this example, we're only considering part of a plane that lies in the first octant. So we have our x, y, and z axes. And to visualize this plane, well, we could find its intercepts with the coordinate axes. So our x-intercept we would find by setting y and z equal to 0. We have 2x equals 6, so x would be 3. To find our y-intercept, we would set x and z equal to 0 in the equation of our plane, and we find that y is equal to 3. And then to find our z-intercept, we set x and y equal to 0 in the equation of that plane, and we find that z would be 6. So the surface of interest is this part of the plane that lies in the first octant. So we're integrating over this little triangular surface here. We'll call that surface S. Now, in order to apply this formula for surface integrals, we need to think about the projection of this surface down onto the xy plane. So if we think about what our projection looks like onto the xy plane, well, we're only working in the first quadrant since our surface was in the first octant. And our x and y intercepts were given by 3 and 3. So if we take the projection of our surface down onto the xy plane, we have this triangular region with vertices at 0, 0, 3, 0, and 0, 3. So this would be what we call D, our projection of that solid down onto the xy plane. We see that projection here in our earlier figure. So in order to set up this surface integral, we're going to make use of the new theorem that we have to evaluate a surface integral in terms of a double integral. Now as part of that theorem, we need to find the partial derivatives of this g function with respect to x and y. So let's think about the function g that we're considering. So in our example, we have our surface is this plane. So if we solve the equation of that plane for z, we have z, which we'll call g of x and y, would be 6 minus 2x minus 2y. So if we find our partial derivatives of g with respect to x and y, we have negative 2, and partial of g with respect to y is also negative 2. So now we're ready to set up our surface integral. So here the surface integral of x over the surface S with respect to surface area can be evaluated as the double integral over the plane region D of our function, which was just x, times the square root of 1 plus the partial derivative of g with respect to x, which was negative 2 squared, plus the partial derivative of g with respect to y, which is negative 2 squared, and then double integral in the plane with respect to area. So let's see what we're left with here. Under the radical, we have 1 plus 4 plus 4, so that is square root 9, or a constant 3, which I can pull out in front of the double integral. And then I just need to evaluate the double integral of x over the plane region D. So let's set it up as an iterated integral. Here we have 3 times, if I think about D as a type 1 region, my outer integral with respect to x would range from 0 to 3, and my inner integral with respect to y, well, y is bounded below by 0, that is the x-axis, and it is bounded above by this line connecting 0, 3 to 3, 0. That is the line y is 3 minus x. So our upper limit of integration for y is 3 minus x. We're integrating the function x in the order dy dx. So we have 3 times the integral from 0 to 3. Evaluating the inner integral with respect to y, well, x is a constant with respect to y. So we have that constant times the length of our y interval, which would be 3 minus x minus 0, or just 3 minus x, integrated with respect to x. So distributing our x, we have the integral from 0 to 3 of 3x minus x squared dx. So for our antiderivative, we had the constant 3 out in front, times 3 halves x squared minus 1/3 x cubed, being evaluated from 0 to 3. So now we have 3 times, when we evaluate at x equals 3, we get 27 halves minus 27 thirds, or 9. So simplifying, we are left with, let's see, 3 times, or 27 halves minus 27 thirds gives us 27 over 6. So we're left with 27 over 2 for the value of this surface integral. So what we're doing here is we're adding up all of the x values of our function over this surface. So let's take a look at one application of evaluating a surface integral. So one application would be in determining the center of mass, or the mass of a surface. So let's say that we have some thin sheet which takes the shape of a surface S, and it has variable density throughout. So let's say the density at any point x, y, z on that surface is given by the density function, rho of xyz. So we would then define the total mass of that sheet as little m. And to find the mass of this sheet, we would take our density function at any given point and evaluate the surface integral with respect to surface area over the surface S, which describes the shape of our surface, or our thin sheet. And that is the mass. So we're adding up the density at every point over our surface to get the total mass. And the center of mass of that surface would be the point x bar, y bar, z bar in space, where x bar is given by 1 over the mass times the surface integral over S of x times the density function. Similarly, y bar is given by 1 over the mass times the surface integral of y times the density function over the surface, and z bar is given by 1 over the mass times the surface integral of z times our density function with respect to surface area. So in this next example, we are asked to find the mass and the center of mass of a thin funnel, which has the shape of a cone. Z equals the square root of x squared plus y squared for values of z between 1 and 4. And the density function is given by 10 minus z. So let's see if we could visualize what our surface looks like here. So in this example, we have a part of a cone. Since z was the positive square root of x squared plus y squared, it's just an upper half cone. So we have z, x, and y. And we're looking at the part of this cone which opens upward and lies between the plane z equals 1 and z equals 4. So in the plane z equals 1, that is 1 unit above the xy plane, we would have the equation x squared plus y squared equals 1. So we would have a circle centered at the origin of radius 1 within the plane z equals 1. And then our cone is becoming larger in radius, the larger that we choose the value of z. And then when z is equal to 4, the upper limit of our z value, we would have a circle of radius 4. So this is our surface S. It's part of a thin funnel here, or it looks like a funnel. So now, if we are asked to find the mass of this funnel, well, we know that we're supposed to evaluate our surface integral over the surface S of our density function, which was 10 minus z with respect to surface area. Now, in order to evaluate this, we need to convert this to a double integral over some plane region D, which would be the projection of our surface onto the xy plane. So thinking about taking the projection of our surface onto the xy plane, let's see what we have. So here, if I were to project the lower part of my funnel down onto the xy plane, we would have a circle centered at the origin of radius 1. And then taking the projection of the top of our funnel down onto the xy plane, we would have a circle centered at the origin of radius 4. So in general, my projection is some annular region bounded by two circles of radius 1 and 4. Okay. So let's see if we can convert this surface integral to a double integral over the region D. So here we have the double integral over d of the function 10 minus z. Now, in our example, the surface z is given by the square root of x squared plus y squared. It's part of a cone. So I replace this z value with the square root of x squared plus y squared. And then I have to multiply by the square root of 1 plus the sum of the squares of the derivatives of that function. So here, differentiating this function, the square root of x squared plus y squared with respect to x, we have, using the chain rule, x over the square root of x squared plus y squared. So I'm then squaring that quantity. And then we add the sum of, or the partial derivative with respect to y, which similarly, using the chain rule, would be y over the square root of x squared plus y squared, quantity squared. And we're evaluating this double integral over d with respect to area. So let's see what we get here. So it looks quite messy at first, but evaluating or simplifying the expression under the radical, when I square this first quantity, I have x squared over x squared plus y squared. And then I am adding, when I square this quantity, y squared over x squared plus y squared. So when I sum those two terms, I have x squared plus y squared divided by x squared plus y squared, which is just 1. So under the radical, I have a 1 plus 1. So altogether, I have a square root of 2, which I can factor out in front of this double integral over d. And I'm integrating 10 minus the square root of x squared plus y squared with respect to area. Now, based off the look of this region D, it's an annular region, it's bounded between two circles. So that suggests that I would likely want to use polar coordinates to evaluate this double integral. So setting this up as an iterated integral using polar coordinates, we have the square root of 2. Our outer integral with respect to theta would range from 0 to 2 pi, since we are making a full revolution around both of those circles to describe our region. And then the range of our radial coordinate r would go from 1 to 4 here. We started with a inner circle of radius 1, and then our outer circle was a circle of radius 4. Now, changing our integrand to polar coordinates, we have 10 minus the square root of x squared plus y squared, which it would be r, times the differential of area using polar coordinates is r dr d theta. So we have the square root of 2 times the integral from 0 to 2 pi, integral from 1 to 4 of, if we distribute our r, we have 10r minus r squared dr d theta. So for this double integral, we can use our usual shortcut approach here. We see that this inner integral with respect to r is constant with respect to theta. So when I evaluate at the endpoints 1 and 4, I just have some constant. So I could pull that out in front of my theta integral, and then evaluating the integral of 1 d theta from 0 to 2 pi, we would have a constant 2 pi. So I have the square root of 2 times 2 pi, and then evaluating this r integral, my antiderivative would be 5r squared minus 1/3 r cubed, evaluated from 1 to 4. So we then have the square root of 2 times 2 pi times, when we evaluate at 4, Let's see, we've got 4 squared is 16 times 5 is 80, minus 4 cubed is 64 over 3. Then we subtract what we get when we plug in 1, which would give me a 5, and then minus the negative 1/3 is plus 1/3. So we are left with, altogether, 108 times the square root of 2 pi for the mass of this funnel with the given density function. Now, the second part of this question asks us to find the center of mass of this thin funnel. And I claim that 2 of the coordinates we can find immediately. So let's see how we could do it. So looking back at our surface S here, maybe outline it in blue again. So we have this funnel, which is a part of a cone. So clearly, looking at the shape of this funnel, it is symmetric about the z-axis. Since this is a cone centered about the z-axis, it's symmetric. And we notice that our density function, rho, is also symmetric about the z-axis. That is, it doesn't depend on x or y explicitly. It only depends on z, how far we're moving upward along this funnel. So using the symmetry of our surface and the symmetry of that density function about the z-axis, we can say the following. So let me say, using symmetry of the surface and the density function, we have 2 of our coordinates, namely x bar and y bar, are equal to 0. Whatever the center of mass of that funnel is, it's going to be within the interior of that funnel and symmetric about the z-axis. So it will be some point on the z-axis itself. Now, to find that z-coordinate, we need to set up the surface integral for that z-coordinate. So here, our z-coordinate, z bar, is given by 1 over the mass. So here, 1 over 108 root 2 pi times the surface integral over the surface S of z times our density function. So that would be 10z minus z squared integrated with respect to S. And then we can set this up as a double integral instead of a surface integral over the same plane region D, using an iterated integral to evaluate. Eventually we can find that our z-coordinate is 65 over 24. So here, our center of mass, x bar, y bar, z bar, is given by the point 0, 0, and 65 over 24. Okay. So in this example, of course, using symmetry, we could find the x and y coordinates for our center of mass were 0. This z coordinate, I just set up the surface integral to give that value for the center of mass, which we could do using work similar to what we did to find the mass. But we can see that these sort of problems get to be pretty tedious to evaluate mass. And then if you don't have symmetry, you've got 3 different surface integrals to evaluate for the coordinates. So I will not ask you to find the coordinates for a center of mass for any problem. I would just ask you for maybe the mass of a surface that has a given density function. So you would just have to evaluate a single surface integral rather than possibly 4 surface integrals for this type of problem. Okay. So in the next part of this section, we will talk about how to define a surface integral for a parametric surface. So recall that the formula that we used for a surface integral in terms of a double integral over a plane only was valid if our surface was the graph of a function, something of the form z equals g of xy. So what about for surfaces which are not the graphs of functions, say a helicoid or something? So we have a new theorem for the surface integral for parametric surfaces. So again, if we have a function f of 3 variables, and its domain includes points on a parametric surface S, which has the vector equation r of uv, where the components are x, y, and z of uv, and the values of our parameters uv are in some plane region D. Then the surface integral of the function f over that surface is again expressed in terms of a double integral over D, where D is the parameter domain describing our surface. And then our function f of x, y, and z is converted to a function of the variables u and v. So to do that, we would just take anywhere we have an x, we take the equation for x in terms of u and v. Anywhere we have y, we plug in the value for y in terms of u and v. And anywhere that we see a z, we plug in the z coordinate in terms of u and v. So we are defining our function f in terms of the vector function r of u and v. And then on the end, we have the differential of surface area. And we had seen in the last part of this lecture that the surface area of a parametric surface is given by the magnitude of the cross product of the partial derivatives of that vector function with respect to u and v. And we are now evaluating a double integral in the plane with respect to area. So for an example of this, we are asked to evaluate the following surface integral of y times z with respect to surface area, where S is the helicoid, which has the vector equation r of uv is u cosine v, u sine v, v, where u ranges from 0 to 1, and v ranges from 0 to pi. So recall a helicoid is like a spiral ramp shape. It's like a bunch of helixes of different radius inscribed within each other. So we get sort of a spiral ramp or a screw shape. And we are asked to evaluate the surface integral over such a surface. So our first step will be to evaluate our function f in terms of u and v. So let's see what we have. Our function was y times z that we're integrating. So taking the product of y and z from our vector function, we have u times v times sine of v. Now, we also need to calculate the partial derivatives of r with respect to u and v so that we can then find the magnitude of the cross product. So our next step here is to find these partial derivatives of r with respect to u, which would be cosine v, sine v, and 0. And partial of r with respect to v would be negative u sine v, u cosine v, and 1. So our cross product of these partial derivative vectors, r sub u and r sub v, would be the determinant of a 3x3 matrix, where our first row consists of the standard basis vectors I, j, k. Our second row consists of the partial derivative of r with respect to u, so that was cosine of v, sine of v, 0, and negative u sine v, u cosine v, and 1. So, evaluating this determinant, we have for our I component sine of v minus 0 For our j component, we have 0 minus cosine of v. And for our k component, we have u cosine squared of v plus u times sine squared of v. So using the fact that sine plus cosine squared of v is equal to 1, we're just left with u for that last component. Now, we can set up our surface integral once we have, let's see, we still need the magnitude of this cross product, r sub u and r sub v. So taking the magnitude, that would be the square root of the sum of the squares. So we would have the square root of sine squared v plus cosine squared v plus u squared. So again, since the square root of sine and cosine squared of some angle is 1, we have the square root of 1 plus u squared. So now we're ready to set up our integral for this surface integral. So here we wanted the surface integral of y times z over the surface S, which is given by the double integral over our parameter domain D of y times z, which in terms of u and v, we found to be u times v times sine of v. So we have u v sine of v times the magnitude of the cross product of those partial derivatives. So we found that to be the square root of 1 plus u squared. We're integrating with respect to area. So setting this up as an iterated integral, we have the outer integral with respect to, if we take our outer one with respect to u, u ranged from 0 to 1. We were told in the problem statement. And then the inner integral with respect to v would range from 0 to pi. Now the function that we're integrating is u times v times sine of v times the square root of 1 plus u squared, integrating in the order dv du. So to make our remaining work a little easier, again, we're going to make use of the fact that we can pull constants out in front of an integral. So for our inner integral with respect to v, we see that u times the square root of 1 plus u squared and du are all constants. So if we were to pull these constant terms out from the inner integral, we are left with the integral from 0 to 1 of u times the square root of 1 plus u squared du times the integral from 0 to pi of v sine of v dv. So then we can find antiderivatives of each of these functions to evaluate the given surface integral. So let's look at our first integral with respect to u. So here we have u times the square root of 1 plus u squared. So a little scratch work to the side here. If we were to use a u substitution, well, we're using u already. Let me make this a w substitution. So if I let w equal 1 plus u squared, then dw would be 2u du. So rewriting this first integral in terms of w, we have 1/2 the integral of square root w dw, and we are evaluating from when u is equal to 0, w is 1, and when u is equal to 1, we find w is 2. So now integrating from 1 to 2. And then we are multiplying by, well, we need an antiderivative for the function v times sine of v. Now to integrate v times sine of v, we would have to use integration by parts. So a little scratch work to the side here. If we were to choose u to be v, and let's see, I better be a little careful here with my notation. So rather than make the formal change of variables, we could use our tabular method for integration. So if we chose our initial value as u to be v, then dv would be sine of v. And integrating this first column, we would have or differentiating the first column, we would have a derivative of 1, and then the derivative of 1 is 0. Integrating sine of v, we have negative cosine of v, and then integrating negative cosine v, we have negative sine of v. So the tabular method for integration is just a shorthand method for integration by parts twice. We match these terms according to the sign plus and minus. And so we have, for the antiderivative of v sine v, negative v times cosine of v plus sine of v, which is being evaluated from 0 to pi. All right. So let's see what we have for this first antiderivative. We had 1/2 the square root of w. So we have half of antiderivative of root w is 2/3 w to the 3/2 from 1 to 2, times, when we evaluate this antiderivative with respect to v at pi, we would have pi plus sine of pi is 0, minus, when we plug in 0 for v, we get 0. So altogether, we are left with 1/3 pi, or pi over 3, times 2 to the 3/2, or 2 root 2, minus 1 to the 3/2, which would be 1. So this would be the value of that surface integral of y times z evaluated over the part of that helicoid whose vector equation was given. So in this part of our lecture, we've introduced the idea of a surface integral of a function over a surface which can be either considered as the graph of a function of two variables or a parametric surface. And we saw that one application of a surface integral is in computing the mass or center of mass of some surface that has varying density throughout. Now in the last part of this section, we're going to define a surface integral of a three-dimensional vector field over a surface and then see some applications.